So we are dealing with sequences right now, and we have to just keep it clear in our mind when we're dealing with a sequence, when we're dealing with a series. A sequence is just an ordered list. A series is a sum of the terms in a sequence. And so usually we talk about the sequence of terms. And we need to be able to apply some descriptions to the sequence of terms. And so here, this slide is all about just some terminology, and it's very intuitive. When you're thinking about an increasing sequence and you visualize it, the terms are getting bigger. So that's what this says. A sub n plus 1 is the term that's right after a sub n. It's the next term. And all we're saying is that if the next term is always bigger than the prior term, we call it an increasing sequence. Similarly, decreasing, if the subsequent term is smaller, if it's less than, then we call it a decreasing sequence. And then we've got these two oddball ones. So we've got non-decreasing and non-increasing. And they are what they say. It's just a little difficult sometimes to keep it straight in your mind. It's very easy to get tangled up. So non-decreasing means it's not going down. It's either staying the same or it's going up, one or the other. So non-decreasing is very similar to increasing. It's just that you can have some flat spots where it stays the same and then it starts trending up. Okay, so non-decreasing means not going down, not decreasing. Similarly, non-increasing means not going up. So it's either staying the same or trending down. And when we're visualizing our sequences, we should be thinking about a function. So we should be thinking, whenever you're visualizing a sequence, this is a decreasing sequence, this is an increasing sequence. So visualize dots in quadrant 1 of the XY plane, and that's how you should be sort of trying to visualize it. Ooh, good question there. Declan, is that from you?
Yeah, that's from me.
We'll talk about that today, because there's a homework question, and they prompt you a little earlier than they should. This is a geometric series.
Great, because I was really confused.
Yeah, it's a yeah, we'll talk about that today. It's tricky. It's going to get really easy today, though, because we'll have a formula for it.
They have like an example for you to look at on the homework, and I looked at it, and now I'm more confused.
Yeah, that example is not great. Okay, so that's the idea between increasing, decreasing, non-decreasing, and non-increasing. And as you know, in math, they love to generalize as much as possible. And that's why they're going to use these two expressions here, non-decreasing and non-increasing. But in practice, it's very difficult to build one of these types of sequences, non-decreasing or non-increasing. It's very difficult to build them. Usually there has to be some funny math going on to allow something to be flat and then go up and then be flat again and then to go up and then to be flat again. 99% of the time, when you see non-decreasing in your mind, you can just say it's increasing. Because the functions that we see, the sequences that we build explicitly with little function formulas, are going to be increasing. If they say non-decreasing, it's totally fine in your mind to say, oh, it's going up, it's increasing. Because to create those flat spots is very difficult mathematically. So you can essentially really just be thinking about increasing and decreasing. Those are the two that are the most important. Just will not see those except with really oddball examples. But as math people, they love to be as general as possible, so they'll say, well, it doesn't have to be increasing, it could just be non-decreasing. But in practice, think of it as increasing. Monotonic means that it's moving in one direction. So it's either trending up or trending down, and it can have flat spots. Monotonic in practice, in your mind, means it's not oscillating. So monotonic means that it's trending in one direction, but if it starts up, it can't then turn around and go down because that would be like a slight oscillation. Okay, so monotonic just means it's trending up or trending down. There could be flat spots, but it's not oscillating. And then we come to this word that we've seen already this semester, bounded. So we can talk about sequences that are bounded above and below. And so remember that we talked about bounded in the context of we were talking about improper integration. And we had those unbounded regions, so unbounded, we couldn't put a circle around something that was unbounded. So if we have a sequence that's bounded above or bounded below, we just mean that there's a horizontal line either above or below or both. If we say the sequence is bounded, it means it's trapped between a ceiling and a floor, if it's bounded. If it's bounded above, it means there's a ceiling and the sequence can't go through it. If it's bounded below, that means there's a floor and the sequence can't go below it. So bounded below, there's a floor. Bounded above, there's a ceiling. And the sequence is in between. All right, so then we're going to have this. So when we look at these two sequences, this red sequence is decreasing, and it's bounded below by 1. So that, and if a sequence is bounded below by a number, it's bounded below by an infinite collection of numbers. Right? You could say this sequence is bounded below by 1, it's bounded below by 0, it's bounded below by -1. So if there's a bound, there's an infinite number of bounds. And if you go on in math, sometimes what they'll talk about is things like if we look at this sequence, let me put it on the board here. If we have a sequence that is bounded above, sometimes it's what you're trying to do. So certainly this is an upper bound for that sequence. It's above it if this sequence is going to stay below it. But it's not necessarily the least of all the upper bounds. So if you go on in math, you'll try to find the least upper bound. The least upper bound will be the one that is the asymptote, the horizontal asymptote. So that would be the least of all the upper bounds. So if something is an upper bound, it doesn't necessarily mean that that's what the sequence converges to. But if this sequence is converging, if this is bounded above, this sequence is going to converge, and it's going to converge to that least upper bound. So a little bit of terminology. We're not going to talk about least upper bounds and greatest lower bounds, but you'll talk about that later in higher math classes. Okay, so the black sequence here is increasing, and it appears to be bounded above by 1. So an increasing sequence that's bounded above has to converge. A decreasing sequence that's bounded below has to converge. Because these sequences have an infinite number of points in them. So if we look at that red sequence, and somehow we figure out that it's bounded below, it must converge. If it's decreasing, it can't bounce up and go away from that asymptote that we kind of see there. Right? So if it's decreasing and bounded below, it has to have an asymptote. It has to have a limit. And if it's increasing and bounded above, it's increasing, so it can't come down. If it's increasing all the way through, and it's got an upper bound, it must converge. So that's going to be a theorem that we are going to see. And I guess it's on the next page, probably. I can't remember now. So does that make sense to everybody? Increasing bounded above, it's got to converge. Decreasing bounded below, it has to converge. Okay, so those are some characteristics of sequences. Now let's get into the most important sequence that leads to the most important series, and that's the geometric. So that is an example of a geometric series up here, 1 over 5 to the k. So geometric means repeated multiplication. You have a common multiplier, a common ratio. And let's just take a look at this one that was written up here on the board, 1 over 5 to the k. What is the first term in this series? 1/5. And then the second term in this series? So 1/25. And so what is the common multiplier that we see for this series?
1/5.
1/5. So 1/5 is the ratio. That's the common multiplier. And the first term in this series is 1/5. So when we get to the point where we're finding the sums of these geometric series, we need to know the common ratio, the common multiplier, and we need to know the first term. That will be enough for us to find the sum of this infinite geometric series. I'll put the formula here. We're going to see it today a lot. So S, the sum of this infinite geometric series is A divided by 1 minus R. Could not be simpler. That simple little formula tells us the sum of this infinite series, which is kind of cool that it's that easy. Okay, so now that's a geometric series. A geometric sequence is a little different, but similar. It's going to have a common multiplier to get from the terms. So if we had this sequence that, say, started at 1/5, this would be an example of a geometric sequence. So same idea. We have a common multiplier, okay? And we have a couple of facts with geometric sequences. So we know that if we take a number that's a proper fraction, it's less than 1, like 1/3, and you multiply it by itself repeatedly, it approaches 0. 1/3 multiplied by itself is 1/9, multiplied by itself is 1/27, 1/5 multiplied by itself is 1/25, multiplied by itself again is 1/125. So that's what this top line is saying right here, that the limit of the sequence is going to be 0 if your common ratio has a magnitude that's less than 1. It's also going to happen if you have negative numbers, like -1/2. If you start with -1/2, multiply by -1/2, you get +1/4, then you get -1/8. You're still going to go to 0, it's just going to oscillate, though, around that horizontal line at 0. So regardless of whether R is positive or negative, you still will have convergence. As long as the magnitude is under 1, you'll have convergence to 0. Now, if R is 1, 1 multiplied by 1 is 1, multiplied by 1 is 1, multiplied by 1 is 1. So the limit, if R happens to be 1, is going to be 1. And then if R happens to have a magnitude that's greater than 1, so magnitude greater than 1, or less than or equal to 1, divergence. So you pick a 2, 2 times 2 is 4, times 2 is 8, times 2 is 16. So bigger than 1 definitely diverges. And certainly less than -1 in magnitude. So if you picked a -2, same thing is happening. You're going to diverge.
Can you also say like absolute value of R is greater than 1?
Well, notice there's one subtlety here, right? If R were equal to 1, you actually do have convergence.
And if it's -1 exactly, then you get an oscillating sequence which does not diverge.
Which does not
Or
converge.
does not converge.
Does not converge, right.
So it can't.
So yeah, when we get to a geometric series, we can say what Zach just said. If the magnitude of R is not less than 1, it will diverge for a geometric series. So let's just talk about that for a moment. Let's look at this weird oddball case here where the geometric sequence does converge if R is 1. If we look at the corresponding series, now I'm forgetting if we use an N or a K in this book. I always, this one is K. So if we have that series, when you look at that series, let's make sure you're understanding what that series means. If you do the sum of 1 from 1 to infinity, if you were to write out the expanded form of this series, it's this, right? And that series definitely diverges. 1 plus 1 plus 1 forever, it's got to diverge. And so we talked about that on Tuesday, that the only way an infinite series can converge, the terms, each term has to be getting progressively closer to 0 at the bare minimum. If the terms are not getting closer and closer and closer to 0, it definitely is going to diverge. And so in this one, it's going to diverge badly, right? 1 plus 1. The terms aren't even going to 0.
But in the case where it is -1 to the k, does that not converge?
No.
Because
So if we have
-1
-1 to the k, then this series looks like this.
Well, it doesn't converge, I guess, because it oscillates. But
So this is going to be, it does not exist.
that's fair.
It's not going to go to infinity or minus infinity. So if we think about how we analyze the convergence of a series, we look at this auxiliary sequence called the sequence of partial sums. So S sub 1 is the sum of just the first term. S sub 2 is the sum of the first two terms, which would be 0. S sub 3 would be what?
-1 again.
-1. S sub 4 would be back to 0. S sub 5 would be back to -1.
Right.
So this sequence of partial sums is going to look like this. And does that sequence converge?
No.
That sequence does not converge because the terms are not getting arbitrarily close to a single number. They're oscillating. So that's why that series would diverge. Okay, so there's just a little visual there. We have divergence, certainly greater than 1 and less than -1, and we also have divergence at -1 for the sequence. Just some pictures. Again, when you're visualizing a sequence, think of it as a function. So the sequence itself is the dots, but every sequence lives inside a parent function that's continuous. So you can always think of the dots within a continuous function. So 0.5 to the x converges to 0. Down here, I built -0.5 to the x here. So the red dots are going to oscillate around 0, but we still have convergence to 0. As long as that magnitude of r is less than 1, we converge to 0. And then here's one that diverges. 1.1 is bigger than 1, so it's definitely going to diverge. 1.1, here I did a -1.1. Or not -1.1, -1 to the 1.1. Still going to diverge, but it's going to diverge by oscillation because we have alternating signs. All right, so let's take a look at this theorem called the squeeze theorem. So the squeeze theorem is going to allow us to mathematically get the limit of something that feels pretty intuitive, but we need a little math to confirm it. So let's just think in our minds for a second. Certainly, if we had the sequence 1 over n, right, this is our basic sequence, and we know that that sequence is going to converge to 0, right? The numerator is constant, the denominator is growing, so the fractions are squeezing to 0, right? Totally intuitive. Now, when you think about this function in the numerator, or this function in the numerator, clearly the numerator is not constant. But it's very close to being constant if you imagine the denominator growing and the numerator is just bouncing around between, let's see, inverse tangent. The lowest inverse tangent ever is -π/2. The largest it ever is π/2. So the numerator is just oscillating, but the denominator is growing massively quickly, going up, 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 up. Intuitively, we know the fractions in generality are going to be getting close to 0. Yes, there's going to be some oscillations for sure, because this is not a constant, and there's positive values and negative values for both of those. But in the big picture, we're going to be, I should go this way, we're going down to 0. So we know intuitively that, yeah, the limit of that, if you plug in 1 for n, and then 10, and then 100, and then 1,000, and then 1,000,000, these this sequence is going to trend to 0. There's going to be some oscillations, but it's going to be definitely going to 0. But that's not the math. So here's how we do the math. We are going to see, and here's the visual for the squeeze theorem. We've got an upper sequence that's converging to L. We've got a lower sequence that's converging to L. And then the black sequence is trapped in between. It must also converge to L. So that's going to be our kind of visual for the squeeze theorem. And here's what we do. We're going to start with the function, and all we need to do is bound the function. And we know that this function is bounded between pi over 2 and negative pi over 2, right? So this function is bounded between negative pi over 2 and pi over 2, means that the sequence is bounded between negative pi over 2 and pi over 2, the inverse tangent sequence. Okay, definitely. Now what we're going to do is divide all sides by n. So what we're going to try to do is just build up so that the middle of this inequality looks like that. So we're going to divide everything by n. And when we divide everything by n, the middle term is getting where we want it to be. And then we're going to apply the limit to that. So we just start with the function, we bound the function, then we try to create the middle term to look like the general sequence term. And then we're going to take the limit, so we're going to take the limit as n goes to infinity. In sequences, we always mean the limit as n goes to infinity. So we're going to take the limit of all three pieces here. And what's true about the left and the right limits?
They both go to 0.
They both go to 0. Because the numerator here is a constant, so we're back into this scenario. Regardless of what that numerator is, if this numerator is a constant, if that's a 4, right, that limit's 0. So if the numerator is a constant and the denominator is growing, we have a limit of 0. So now we're in this situation here. So we get 0 on the left. We have the limit in the middle of arctan of n over n, and we have a 0 on the right. So therefore, the limit of arctan n over n has to be 0. So the squeeze theorem is what allows us to put math behind the intuition that if the numerator is just flopping around between, in some interval, and the denominator is growing without bound, that limit's got to be 0. So it just puts a little math behind it. So it proves it to us. But this should add to our intuition. If we have a numerator that's bounded and the denominator is growing, the fractions have to go to 0. The limit has to be 0. What are the bounds for cosine of n?
1 and negative 1.
So we're going to do the same type of thing. We're going to say, oh, okay, we can bound cosine. And then let's build the middle term so that it looks like the general sequence term. Bless you. So we've got that. And then we're going to apply the limit to everything. So we're going to take the limit of the left, the limit of the middle, and the limit of the right. And that limit is as n goes to infinity. Because we're dealing with sequences, that's the only limit that makes sense, is to go to infinity. And again, what do we have as our limits on the left and the right?
0.
Yeah, 0. Both have constants in the numerator. And so if they both have constants in the numerator and the denominator is growing without bound, we get the conclusion we're looking for. So now we know that the limit of cosine of n over n is equal to 0. So that's the squeeze theorem. Puts math behind these ideas.
On like an exam, if we were to be boxing our answer, would we just box that last bit of limit n approaches infinity? Do you need the therefore and the reasoning?
You could, yeah, either of those is fine. Yeah, you can put a box around all this stuff. I mean, this is one of those funny ones where that's more important, right? Because you are trying to prove that this limit is 0, so the work is going to be to generate that conclusion. Okay, so a little more terminology. This is what I was talking about a moment ago. And even in their pictures. So monotonic means it's trending in one direction only, there's no oscillation. And non-decreasing, but what have they shown us? That's not a non-decreasing, I mean it is non-decreasing, but more precisely it's actually increasing. So in this class and in most math classes, if you see it non-decreasing, you can just replace it with increasing. You can just replace it by increasing, because this is what we are going to see in practice 99+% of the time. So here is that theorem. If it's bounded and monotonic, it must converge. So this is an increasing sequence, which makes it monotonic. It's bounded above. That means it has to converge. This one is decreasing, which is monotonic. It's not oscillating. It's bounded below, so it has to converge. And again, there's an infinite number of upper bounds for this left one, an infinite number of lower bounds for the right-hand one. The limit of this sequence would be the least of all the upper bounds. It would be that asymptote that they've kind of implied right there. And similarly down here, the limit of this sequence will be the greatest of all the possible lower bounds, which they are implying is that n.
It also theoretically needs to be increasing and not non-decreasing, because it could eventually reach a point where it's just flat and not at the asymptote kind of thing.
Well, if it gets flat, if it gets flat forever, then it's
Gotcha.
that it's sort of not then it's not going to be in the it's not going to be an asymptote because it's actually equal to the limit.
Yeah.
You know, it's kind of like this sequence over here. This sequence right here, 1, 1, 1, 1. This converges to 1. So we wouldn't call it an asymptote in that context.
Gotcha.
So if the sequence is increasing or decreasing in bounded, then it does act like an asymptote when you're looking at the graph. But if it's got those repeated values, then we wouldn't call it an asymptote. It would just be the limit. Now, we are going to be dealing with some functions that we don't know how to take limits of with standard methods. You know, things like factorials and power towers. And one of our common limit techniques is the derivative, is L'Hopital's rule, where we take the derivative of the numerator and the derivative of the denominator. When we have some of these oddball functions like the factorial function or the power tower, those two in particular, we don't know how to differentiate those functions. You can't differentiate n factorial or n to the n. Let's just make sure everyone understands what n factorial is first. So if we have something like 6 factorial, that is repeated multiplication down to 1.
What's the parent function of the factorial? Like, what does it live in?
The gamma function.
Oh no.
No.
So, great question. So the factorial function, believe it or not, has a generalization called the gamma function, and it's a continuous, there are some discontinuities in it, but it's a continuous function for the most part that matches at all the factorial spots. Yeah, if you graph the gamma function, you will see,
Something gnarly.
yes, you will see something. There is a lot of math research on the gamma function because it remarkably does what we just mentioned.
Can you differentiate the gamma function?
There it is. So the gamma function, it's continuous. Like if we look at the positive integers where we're talking about factorials, it's continuous over there. On the left-hand side, there's these asymptotes where it's not continuous, but we don't care about those negative numbers. But over here, if you look at all of these intersection points, like 2 factorial is 2 times 1, which is 2. There it is. 3 factorial is 3 times 2 times 1, which is 6, which is right there. 4 factorial, we just keep on doing this multiplication, and we're going to get 4 factorial is going to be 24. So the gamma function is where we care about it is continuous. And it matches the factorial function. So you can technically differentiate it because it's smooth, it has tangent lines, but we don't know how to do it. So what that tells us then is that we need another technique. And this technique is much more heuristic. It's much more, kind of not mathematically sound. We say we're waving our hands a little bit. If you go further on in math, you can get more precise about this. But here is what we're dealing with. So also power tower, x to the x. So this is an interesting thing. When I was in grad school, the power tower, x to the x, normal mortals had always differentiated that with the log derivative process, like you should have learned in Calc 1. You let y equal x to the x, you take the log of both sides, you use implicit differentiation, do some back substitution, and you would get this derivative using the log diff process, log derivative process. When I was in grad school, there was a high school student that showed that you could differentiate the power tower by first treating it like a polynomial. And so taking the derivative as if it were a polynomial, even though it's not. And if it were a polynomial, you would bring the power down and subtract 1 from the exponent. And then adding the derivative if you've treated it like an exponential function. If you treated it like an exponential function, the derivative would be itself times the derivative of the exponent. And that remarkably works. If you first treat it like a polynomial and then treat it like an exponential, you will get the correct derivative that you would get if you take the log derivative process. Totally crazy. And that's not how you spell derivative. The log derivative process. So for our purposes though, we are not going to be differentiating power towers or factorials. But what we need to know is this growth rate concept. So here are the 5 main functions that we're dealing with. And they do some oddball stuff in here where they combine a log with an exponential. We really don't care about that. Powers of logs, we're going to keep it very simple. These are the 5 categories of functions that we're dealing with. And that double greater than means the one to the right grows significantly faster than the one to the left. So when we can't do the math, we just apply this growth rate concept. And so what it means is that a power tower is going to grow significantly faster than a factorial. So if the power tower is in the denominator, it's the dominating one. It goes to infinity faster than the numerator. So what's that limit going to be?
0.
0. So this is going to go to 0. And we can't do the math, so we just say by growth rates. Now, if we can do the math, we do it. If we can use L'Hopital's rule, we do it. Unless we had to do it 1,000 times. So like this one, you might say, oh wait, we could do it. We could do L'Hopital's rule. But you'd have to do it 1,000 times. So if you're in a situation like that, we will just use growth rates instead of doing L'Hopital's rule by 1,000 times. So this is also going to go to 0 because this numerator is a polynomial. It doesn't matter how big that exponent is. If that exponent were 10 billion and this were still just 2 to the n, the limit is still 0. It may take a really long time before that denominator overtakes that numerator, but eventually it's going to overtake the numerator and drag it all to 0.
It's almost like a trillion x versus 0.2x squared.
Mm-hmm. that x squared is going to take over eventually. Yeah, no matter how steep your line is, if you do a trillion x and it's wicked steep, eventually the quadratic will take over. But you'd have to go very high up in the y values to see it. But eventually it will take over. So, same idea in this case. That's an exponential. That's a polynomial. The exponential wins. Now this is an exponential growth, not an exponential decay. So it's not 1/2 to the n, that's totally different. If that's an exponential growth, if these are both going to infinity, that's exponential growth, that is going to take over. So that's going to also approach 0 by growth rates. So when we can't do the math, we just apply the growth rate idea.
This is a very good reason why you can't just look at a graph and assume that it goes to infinity because the graph looks like it's going to infinity, because it will be going to infinity for a very long time, but eventually it will drop back off.
Yeah, graphs are a little, I mean, they're super and they're fantastic, but we just can't put too much stock in them sometimes, especially when we're not zoomed way out. You know, when we're real close to the action, you can't quite see it all. Okay, so this is basically the Calc 1 definition. Calc 1, you just called it the definition of a limit. Here we talk about the limit of a sequence, but it's the same idea. And so we talked about the idea of it last time. If you have a function that has a limit, so you imagine L being the limit of this sequence. Sequence is a function. So if you imagine this function, the sequence having a limit, what it means to have a limit is that no matter how small you pick epsilon, so you're creating this little epsilon tunnel around L, eventually there has to be an n, a capital N on the x-axis, for which the sequence is trapped inside that little epsilon interval, epsilon strip, epsilon tunnel, however you want to think about it. So as epsilon, so the idea is that this is true, for the limit to exist, this is true for every single epsilon you pick. And so the idea is that as you start ratcheting the epsilon down, you're shrinking the height of that little tunnel, you have to go further out in the sequence so that the tail is trapped inside that little tunnel. All right, so that's what it means for the limit to exist. For the limit to exist, it doesn't matter how small you make that tunnel. If you go far enough out in the sequence, eventually the rest of the sequence is bouncing around inside that little epsilon tunnel. You know, so as we ratchet this epsilon smaller, it creates a smaller tunnel, and that means we're going to have to go further out in order for the rest of the sequence to be within that tunnel. Okay, so that's the formal definition of a limit. We're not going to use it, we're just going to use the idea of that. But that's what it means for this sequence to have a limit. For any epsilon, you're going to eventually have the tail within epsilon of L. Okay. So we'll spend one slide talking about some of these recursive sequences. Recursive sequences are kind of an anomaly. We're not going to look at them in great detail. More interesting are the function sequences, the functions that are generated by a sequence. But there are some interesting things with these recursive ones. So as we talked about last time, when you define a sequence recursively, you've got your formula piece here that tells you how to get to the next term from the prior term. But you also have to know where you're starting. So you have to be given some initial value to start the iterative process with. So we start with 2. There's our sequence term. And then we take that 2, we plug it in here and here, plug it in right there, plug in the 2, simplify it, we get 1.5. So that's the next term in the sequence. Do it again. Take this whole thing, take that 1.5, plug it back in there and there, simplify it, we get that. Take that, plug it back into the sequence, simplify it, we get that. And so with the recursive ones, what we said last time was that if we're reasonably convinced that it converges, we can find the limit by using that little algebra trick. So let's see what happens. When we look at this, if we went out a couple more terms, it certainly looks like we're starting to zoom in on 1.41 something or other. Square root of 2, possibly. Let's take a look. So we're going to assume that the limit does exist. So we're just sort of looking at some data. We're like, oh yeah, it feels like that limit exists. So we're going to assume that the limit of a sub n is L. We're going to say the limit of the sequence is L. So if that's true, then we're going to take the limit of both sides of this equation right here. We're going to treat it like an equation. We're going to take the limit of both sides. And when we take the limit of both sides, we're going to get an algebraic equation. So once again, if the limit of a sub n is L, that also means the limit of a sub n plus 1 is also L. Because we're thinking of these as sequences that are separate. We're thinking of the a sub n sequence starts with a sub 1, a sub 2, a sub 3, a sub 4. The a sub n plus 1, it's still a sequence. N starts at 1, so this one is just starting with a sub 2, a sub 3, a sub 4, a sub 5. So it's the same exact sequence except it's missing the first term, which has no bearing on the limit. The limit is all about the tail. And so when we take the limit of both sides of this equation, we end up with L equals, and remember the limit can pass through continuous functions. It can jump to the middle here. And we end up with L plus 2 over L. Take the limit of each of those. End up with an algebraic equation here. Let's multiply both sides by 2 just to clean that up. So we have that. We can subtract L from both sides. So that's what we get if we subtract L from the left and the right. Let's come up over here. That's going to give us L squared equals 2. Take the square root. We get plus or minus root 2. All these terms are positive. So there is no chance for a negative. So that means the limit must be positive if it does exist. And that is the limit. So if we have a recursive sequence that converges, we can use this algebraic trick to find the limit. So pretty clever. So same idea with this one. We're looking here. We've got this recursive formula, this recursive definition. We're starting at 3. Plug it in, then we get square root of 5. Plug square root of 5 in there, we get that. Plug that into there and repeatedly, and it certainly looks like we're converging the two if we just look numerically. But to do the math, again, we're reasonably assured that it converges, so we're going to assume that the limit of a sub n is L. Which means the limit of a sub n plus 1 is also L. Because a sub n is a sequence, a sub n plus 1 is the same sequence with the first term chopped off. So that also has a limit of L. So we take the limit of both sides of this equation here. We treat it like an equation. We just take the limit of both sides. Got that. Oh, whoops. We don't want to take away, haven't evaluated the limit yet, so that's still a sub n. And then we take the limit. Once again on the right, the limit is very stealth. It can move through continuous functions. The square root is a function that is continuous. We know what square root looks like. It's continuous. The limit can squeeze right through it. And so this will end up being the square root of 2 plus L. Square both sides. Move everything to the left. You get that? Factor. This tells us that L is either -1 or 2. And how do we know it's not -1? because this is a positive square root, so the values are always positive. There's never a negative value in the sequence, so this tells us that the limit, so therefore the limit must equal 2. So this little algebra trick works great if you have a recursive sequence that converges. Now if you have a recursive sequence that doesn't converge and you do this algebra, you'll get a number usually, but it's meaningless, at least as far as we can tell. So this process will work, but you have to have a sequence that does converge for it to be meaningful. All right, any question on that idea? Okay, so now we've got sequences dialed. Now the heart of the section, the heart of the chapter, I should say, infinite series. So over this weekend, make sure you get caught up, get all that 10.1, 10.2 preliminary homework done, because infinite series is the heart of chapter 10. Okay, so once again, we start with the sequence of terms. We usually call that sequence A sub n. So A sub n is just a big list of numbers. And then we decide to add them together because just having a list is boring. We want to combine them. We want to merge them into one big number if we can. So the series is the summation, capital sigma, it's the summation of all the terms in the sequence of terms. And then we learned that to analyze a series, we create a second sequence. And the second sequence is the sequence of partial sums. So the sequence of partial sums is where we slowly creep to the right. Start with the first term, then we take the first 2 terms, then we take the first 3 terms, then we take the first 4 terms. So the sequence of partial sums is sort of creeping towards adding all the terms together. Just take it one step at a time. So that's what this visual is showing. S sub 1 is the first term, S sub 2 is the first 2, blah, blah, blah. If the sequence of partial sums happens to have a limit, then the series converges and is equal to that number. So if the sequence of partial sums converges to L, then the series equals L. So that's it. That's infinite series in one slide. One slide.
Easy.
Right? Seems easy. Seems easy. Now again, what I mentioned last time, which I'll say again because it's so important, most series will not be friendly. Most series are like piranhas, and they will not allow the formulation of an S sub n. We can't get our hands on an S sub n. If we can get our hands on a function that represents the S sub n sequence, all we have to do is take the limit. And we know how to take limits. But most series will not have an S sub n that we can find. So very difficult or impossible to find. There are 2 exceptions that we are going to look at in detail. Geometric series, we can find S sub n, and telescoping series. We'll talk about those later today. So there's only 2. Of all the series that we're looking at, there's only 2 types that we can find S sub n. All the other ones we cannot find S sub n. Geometric and telescoping. First we will hit geometric. So geometric series. So geometric series will have convergence. Like Zach, what you mentioned earlier, you said, can't we just say that it converges if R has a magnitude less than 1 and diverges otherwise? Yes, if we're talking about a geometric series. For a geometric sequence, we have that one oddball case that if you plug in R equals 1, you actually get convergence. For a geometric series, you get divergence, though. If you add the ones, you get divergence, but if you're just comma-ing the ones, you get convergence. But when you're adding them, which is a series, you're going to have divergence at 1 and to the right. You will have divergence at -1 to the left. So we are going to have convergence when the magnitude of the common ratio is less than 1. Otherwise, diverge. And this is nice about a series. It either converges or diverges. There's nothing else. It's one or the other. If it's not converging, it's diverging. So one thing I want you to notice here is that it's converging on an interval centered at 0. And we are going to see this pattern generalized where we will have an interval of convergence that has a central point and there's some symmetry around that central point. We're going to see that that this idea will generalize. Okay, so first off, let's take a look at our expanded geometric series. So here's a general geometric series. Most of the time, geometric series start at 0. And the reason for that is that you can get a first term that is a constant, so you can start at whatever term you want. You can start with a 1/5, a 5, a 12, whatever. And then your common multiplier is going to take you from the first term to the second. So the common multiplier here is r. We're just going to keep on multiplying by r. So the first term is a, right? R to the 0 is just 1. So the first term is a, multiply by r, multiply by r, multiply by r repeatedly. That's our geometric series. So it has this arc form, ar to the k. Okay. Now the a is common to all terms, so if you wanted to, it's totally legitimate. You could factor out the a, and then over here, if you factored out the a, you're thinking about the a there. And again, this term r to the 0 is just 1, so you can think of that as a 1 if you want. All right, r to the 0, 1. And this would be kind of the, the factored form of your geometric series. So those are just some things you can do with it. You can factor out if you want. So S sub n is the sum of the first n terms. When the series starts at 0, the indices will not align. S sub 1 is a sub 0. Right? If we're looking at the form of this series up here, and I write it in this form, if we're starting at 0, then the series in expanded form is going to look like this. S sub 1 always corresponds to the first term. It doesn't care what the index is. If the index starts at 0 or starts at -5 or starts at 50, does not matter. S sub 1 is the first term. It's easiest if the series was a sub 1 plus a sub 2 plus a sub 3, because then S sub 1's index would match the a's index. S sub 2 would be a1 plus a2, like the indices would match. But if they don't match, you just have to be a little careful. So that is S sub 1. S sub 1 is a sub 0. S sub 2 is a sub 0 plus a sub 1. All right, so there's going to be a little shifting of the indices. S sub 2 means sum of the first two terms. Doesn't matter what the indices are. You just add the first two terms. Okay, so that's why here S sub n is the sum of the first n terms. That's why there's this shift here. That power is not going to be n because we started with 0. So we have to stop one before we get to the power of n term. So there's S sub n. Simple. Multiply by r. All right, we know how to multiply by r. So we're going to multiply both sides by r. So multiply that side by r. So this side is just r times S sub n. We multiplied by r. This side we multiply by r, so we distribute the r. Now we have all that. Now what we're going to do is subtract these two. So we're going to do S sub n So left side's that minus that. And now on the right side, if you do upper expansion minus lower expansion, you have a zillion term, well, no, you have a bunch of terms that are canceling, right? All these terms are canceling. That one's going to cancel with that. Everything in the middle is canceling. The only terms that aren't canceling are those two. So we have that. We're back to algebra 1. Factor. We can factor out S sub n here. Right? This is S sub n times 1 minus r. Factor out the S sub n. Divide by the 1 minus r. We now have a formula for S sub n for any geometric series. That is our formula for S sub n for a geometric series. Now, we already talked about the convergence of a geometric series occurs when the common ratio's magnitude is under 1. So if r is under 1 in magnitude, if it's less than 1 in magnitude, r to the n goes to 0. Right? If r is less than 1, think of an example, 1/2. 1/2 times a half times a half times a half, that goes to 0. So r to the n, right here, that is going to go to 0 if the magnitude of r is less than 1. Okay, that part's going to 0. Now we have the sum of a geometric series with this simple little formula, a divided by 1 minus r. Shockingly simple when you're adding up an infinite number of terms. A over 1 minus r, that's the sum of the infinite geometric series. In other words, it's a heck of a lot easier to find the sum of an infinite geometric series than a finite geometric series. S sub n is the first n terms. Adding them together, you've got this extra pesky term of r to the n. So S sub n is going to be harder to find than S. So, and this is where Declan's question comes in. And all geometric series you can find S sub n. And if you are clever, you can find the pattern here without that formula, but it's very tricky. It's very tricky. So S sub 2 is the sum of the first two terms, so you'd multiply by 5, we get 6 over 25. S sub 3, we're going to add the sum of the first three terms, so we're going to add the sum of the first two, so we're going to multiply by 5, so it's going to be, I think, 31 over 125. And for a geometric series, it is very, very difficult to see what the pattern is here. But, long story short is, all we have to do is that. And so the homework gives you this a little bit earlier than they should, but it's totally fine if you want to use that formula. So your S sub n for this geometric series is going to be, let's see, what's A? 1/5. A is always the very first term. So regardless of anything else, that is always A. And then if we put in the numbers here, this is going to be 1 minus, the common ratio is 1/5. So 1/5 to the n divided by 1 minus the common ratio. So that is the S sub n. And it is possible to generate that by being very diligent in pounding your head to figure out this pattern here. It's not worth it though, unless you really are over ambitious. You can just use that formula. That will find your S sub n.
You still have to solve that, right?
We would still have to solve this. Yeah, we can simplify this quite a bit. So what we could do here, we have the 1/5 out in front. And what is 1 minus 1/5 is 4/5. And we're dividing by the 4/5, so we would end up multiplying by 5/4. And then we have this 1 minus 1/5 to the n, and that n, 1 to the n is just 1, so we could put the n on that 5 down there. So we have this. So when all is said and done, we have 1 minus 1, we have this. I can't even say it. So that would be simplified right there. And what is the limit of that as n goes to infinity? 1/4. Because this 1 over 5 to the n is going to go to 0, so the sum of this is 1/4. Now, if you are super ambitious and you want to sort of try to understand how to get to this, here is the clue. If you look at the geometric series, if you look at this one, if you just do like 3 or 4 of these, you are going to notice that it is 1 less. This number that we get right here is going to be 1 less than that number. That is going to be the pattern, which is very hard to notice unless you write out 4 or 5 of them. Then you can start to see that that number in the denominator is always going to be that, and then one number in the denominator, one notch, 1 pip less in the denominator. Yeah.
Yeah, so the book tried to do some, for lack of better words, some fuckery.
Yeah.
And are you ever going to require us
No!
to do that?
No effery in here. No. Yeah, no, the way that they do it in that problem is really manic. And it's true what they do, but it's
A mess.
a mess. Yeah, and the homework just has you do this one to get you to think about it, but literally it's totally fine, even in that sec, just use this. Just use that. So that's going to be going forward from now on, just use that partial sum formula.
You can kind of see in the S 1, 2, and 3 that if you just subtract 1 off of the denominator every time,
Yeah.
you end up at exactly a 4th.
Exactly.
So-
Exactly. So what you will see is that whatever your pattern is for the denominator, so in this case it's going to be, the denominator is going to be 5 to the 3. The numerator is always going to be a multiple of 5 to the 3. So 5 to the 3 minus 1. So if you take that 5 to the 3 and subtract 1, this number will be a multiple of that. A fractional multiple, but it will be a multiple of that. Yeah, that's right. All right, let's stop there, take 10, and then we'll do some geometric series.
Doing well volunteer work is
It's work.
Yeah, but
Volunteering.
that has an additional
shows
caveat
up
to
on
it.
Yeah. It's
But it's
it's
still
working
work.
with extra steps. The extra steps being you don't get paid.
All right, so let's talk about indices here. I just mentioned this a moment ago that you just have to be careful with these indices. In particular, if your series is starting at 0, your S sub 1 is going to be that first term right there. So there's S sub 1. So these indices aren't going to line up. So I just picked a random divergent geometric series. So I chose an R value of 2 and an A value of 1 and plugged it into all this stuff. So there's our S sub n. If we happen to have a series that has an A value of 1, we plug in a 1. If the ratio happens to be 2, here is your S sub n. So this tells you the sum of the first n terms. So if you want the first term, the first partial sum, if you plug in 1, bingo, right there, you get 1. If you want S sub 2, you would plug in a 2, 4 minus 1 is 3. So this formula is going to find your S sub n's for every n. Just be careful, again, because if that's a 0 and that's a 1, things are shifted. So the sum of the first 4 terms, this is going to be an A sub 0 in here, and then an A sub 1, and then an A sub 2, and then an A sub 3. So A sub 3 is going to be the last term in S sub 4. You just have to remember that. Other than that, it's fairly straightforward. Okay, so that's just reiterating that be careful thing. So let's do a couple of geometric series. This is a finite geometric series. We see that there's not infinity. We assume it's infinite unless it shows us otherwise. So clearly that's not an infinite geometric series. So I want you to tell me what, bless you, tell me what A is for this finite geometric series. A always represents the very first term. So the very first term is found by plugging in the initial index value, which is 4. So the very first term is 2 to the 4. So we get 16. 16. Not 4 to, not, yeah, 2 to the 4, 16. How about the common ratio? 2. If there's any question in your mind, just write out the first few terms. If there's any question, so let's write out the first few terms. We plug in, we get 2 to the 4, plus then 2 to the 5, and then plus, and that's going to keep on trucking, right? So let's move that up there. And this is going to keep on going all the way until we get up to, we're going to have 2 to the 11, and then we're going to have a last term of 2 to the 12. So there are the terms. And you can see, to get from here to here, you multiply by 2. So that tells you your common ratio is 2. Okay. Now, with a finite geometric series, you need one other number. For an infinite geometric series, we had, I guess I erased it. We have S equals A over 1 minus R. So for an infinite geometric series, there's only 2 numbers you need. But for a finite geometric series, you also need the n value. You need to figure out how many terms are in that finite sequence of terms that are being added together. And how many are being added together?
8.
No.
8? 9, right?
Okay, so let's... How many terms are right here?
2.
And that minus that is 1.
Yeah.
So it's always going to be 1 more than that minus that.
9.
Right? So it's the idea of counting fence posts versus counting panels. If you've got 2 panels, you've got 1 more fence post to hold them up. It's that idea. So if we do 12 minus 4, that's going to count the panels in between the posts, but we'd have to add 1 more to that to actually get the number of terms. Okay, so that gets kind of a little heady though. If you wanted to, we could re-index. Like it's super simple if the index started at 1. If the index starts at 1, let's just suppose we have a geometric series, and let's just suppose we started with 1. And if we've got that geometric series there, it starts at 1. Actually, let's make it a finite one, since that's what we're dealing with. How many terms does this one have? 5, because we start at 1. Right? We're going to have the first term when k is 1, and then the second term when k is 2. When we get to 5, yeah, right? We're going to have 5 terms. So if it starts at 1, so think about it this way. What do you do to the 4 to get to 1?
Minus.
Subtract 3. So if you subtract 3 from the upper number, you get 9. That's going to be the number of terms. So you could do it that way also. So you could do upper minus lower, add 1. 12 minus 4 plus 1 is 9. Or you could say, how do you get to 1 from 4? You subtract 3, and if you subtract 3 up there, you get 9. And then you'd be in this case over here. So if you can make the counter start at 1, then the upper number is the number of terms. The counter is counting the terms, literally. Okay, so n is going to be 8. So however you want to think about it, you just have to get to, I said 8, 9. So n is going to be 9. So however you get to it is totally fine. And then the sum of this finite geometric series, now we can use our formula right there. So it's going to be a, which we said is 16, multiplied by this fraction 1 minus, common ratio is 2, the number of terms is 9, over 1 minus the common ratio. And then we just have to simplify that. I see that the denominator turns into a -1, so this could be pushed into the numerator, and we could make that 2 to the 9 minus 1. And did someone enter that into their calculator? 2 to the 9 minus 1 times 16.
8176.
8176, thank you. So that'll be the sum of that finite geometric series. Okay, let's try another one here. So let's first identify A, R, and N. What is A in this case? A is the very first term in the series. So we look at the initial index to get the initial term. When k equals 0 is plugged in here, we have pi to the 0, which is 1. And then how about the common ratio? Pi is the common ratio. Pi is always going to be the base of the exponential expression that you have here. Now I'm going to just write this one out because we don't have that many terms. How many terms do we have, in fact?
7. Because k is starting at 0, so you have one, right?
Yep.
So if I write them all out, it's easy enough to count them. 1, 2, 3, 4, 5, 6, 7. Or you do 6 minus 0 plus 1. Or you say, how do I get the k to be a 1? If we add 1 to that 0, we get 1. And then we add 1 to the upper limit, add 1 to the 6, and we get a 7. That tells us the number of terms is 7. So whatever it takes. And then this will be A, which is 1, multiplied by the fraction 1 minus r to the n, which is 7, over 1 minus r. And that's what we get. So there's our, usually we're not going to type this in because it's going to be irrational. So we can just leave that as our sum. If you wanted to, you could divide numerator and denominator by 1 if this looks better to you. It looks better to me. You could do that. And pi minus 1 will actually divide evenly into pi to the 7 minus 1, but we don't need to do long division in here. Okay, any questions on that partial sum, i.e. finite geometric series stuff? So here, approximate to 2 decimals using Desmos or a calculator. Let's first again identify A, R, and N. What is A? So the initial term is found by looking at the initial index value.
Pi to e over pi squared.
E over pi squared.
Or e squared over pi squared.
E squared over pi squared. There's our first term. Now, if this was an infinite geometric series, would it converge or diverge? If it was infinite. So we would look at the common ratio. The common ratio is e over pi. Is that less than 1 or greater than 1?
Less than.
Less than 1, 2.7-ish divided by 3.1-ish, that's less than 1. So this would be a convergent infinite series if it did go to infinity. How about this one? If this was infinite, would it converge or diverge with that common ratio?
Diverge.
So that's greater than 1, so this would be a divergent infinite series. And this one would be converge or diverge for this infinite series. So that R value also bigger than 1, so it would also diverge. So anytime that common ratio is bigger than 1, the infinite series would diverge. The finite series always converges, right? It's a finite series. You're just adding a finite number of numbers together. So it has to converge. Okay, how many terms in this one? 49. Again, you can do it in several ways. 50 minus 2 plus 1. Or subtract 1 from the 2 to get to a 1, and if you subtract 1 up there, you get to 49, and then it will be a counter. So that upper number is your magic number. Okay, so this is going to be A, which is e squared over pi squared. There's A. multiplied by the fraction 1 minus r raised to the n power, which is 49, over 1 minus r.
Gross.
5.552.
5.552.
Yeah.
So if we go to 2 decimal places, 5.55. Everyone okay with that?
On the exam, are you gonna let us know or ask us for geometric sums or?
I will ask you for infinite geometric sums for sure. Finite geometric sums, probably not. You know, we're much more interested in the infinite part of it, but this is, so probably not a finite one. We'll talk about it though during review, just to make sure. I will definitely tell you whether it will be on there or not. Okay, so now let's go to the infinite ones. We need a lot less space. The infinite ones are easier. So, a over 1 minus r. So let's do this one first. What is a in this for this one?
1.
So a is 1. Plug in our initial value. 1/4 raised to the 0 is 1. And what is the r value? 1/4. So the sum of this series is a over 1 minus r. So we get 4/3. We prefer the infinite series. A lot easier. How about this one? What is the a value and what is the r value?
A
A is 1.
R is 1 of 5.
A is always the first term, and whatever you multiply the first term to get the second term, that's got to be the r value, so 1/5. And then our s, the total sum, is going to be a over 1 minus r. If we multiply everything through by pi to clear the fraction, we would have that as our total sum. Kind of funny that the infinite series is so much more manageable to find the sum of than the finite one. Okay. What is a for this one? 5/4. Totally agree. And what is the r value for this one?
5/4.
So the r value is going to be 1/2. Let's make sure we understand why. So if we were going to write this series in expanded form, we would first start with 5/4. And then when m goes to 3, we would add 5 over, if m is 3, 2 to the 3 is 8. And then we go to the next term, so there, m was 2, m was 3, now m is 4. We're going to have 5 over 2 to the 4th, which is 16, plus etc. So there's the expanded form of the series. The common ratio tells you how you get from one term to the next. We are multiplying by 1/2 repeatedly. Everybody see that? Now you might say the 5 is a constant. Can we factor it out to the front? And the answer is yes. If you wanted to, you could factor that 5 to the front, find the sum of that geometric series, and then multiply by 5. Totally fine to do that too. Okay, so our sum for this one, a over 1 minus r, so the a goes in the numerator, and then 1 minus the common ratio. 1 minus 1/2 is 1/2. Dividing by 1/2 means multiplying by 2, so we get 5 over 2. So that would be the sum of the series. So this one, A is 1/16. We just grab that very first term. So if it's in expanded form, it's especially easy to see A. And then the common ratio.
3/4.
So we certainly are going to start out with 3/4 because we look here, and that's pretty obvious that we multiplied by 3/4. Let's just double check. If we multiply again by 3/4, do we get the next term? Yeah. 3 times 3 is 9. 4 times 64 is 128 times 2, which is 256. So it's true. It's geometric. And then our S value, the sum of this series, is going to be A, 1/16 divided by 1 minus R. So we have a 3/4 down here. Lots of ways to do this. I'm going to multiply through by 16 just to clear all those fractions real quick. So I multiplied everything by 16. And then we get our final answer of 1/4. So, how we find infinite series? The sum of an infinite series that's geometric.
Not too bad.
Not too bad. Not too bad. Yeah. Geometric series are very tangible. You can get your hands on them really nicely. Let's just do a couple that have some few little twists. So we look at this geometric series number 23, and let's identify A and R. So A is 1. Everyone agree? Plugging in a 0 for that exponent. Any number to the 0 other than 0 is 1. How about the common ratio? Negative 9/10. So is this infinite series going to converge or diverge?
Converge.
So that common ratio, as long as that magnitude is less than 1, the magnitude of that is 9/10. That is less than 1, so we have convergence. Definitely going to converge. So the sum of this is going to be A over 1 minus R. What's that?
19, or no, 10, 19.
Let's see, if we multiply everything by 10, multiply that by 10, multiply that by 10, that's a plus, multiply that by 10, we get 10/19. Okay, will this one converge?
Nope.
So let's identify A and R. So A, what's A here? So A, we plug in the 1 there, so we're going to get 1 over negative E, so we could write that as negative 1 over E. Everyone agree with that? So we're plugging in 1 right there, a negative 1 exponent, you reciprocate, so 1 over negative E. And what's the common ratio?
Negative 1 over.
So let's rewrite this. So the common ratio is super obvious if the exponent is just k. If the exponent's not just k, let's modify it a little bit so that the exponent is k. So we know that a minus 1, we're going to treat it this way. We know that that minus 1 is going to reciprocate the base. So we're going to first, if we do all the math, we're going to do that. Let me also point out, with these infinite series, if we know we're dealing with an infinite series, it's totally fine to shortcut the notation and just write a 1 there. We know it's going on forever. So you can shortcut it, it's totally fine. And everybody, is this all good with everyone? When you have a power to a power, you multiply. So that is going to allow us to rewrite the summand as, let's see, negative 1 over E. all raised to the k. So now we see our common ratio really nicely. If we have the exponent just being k, the common ratio is whatever the base of that is. So that tells us that our common ratio is in fact -1 over e. That is less than 1 in magnitude, so it will converge. And the sum of this series will be a, so minus 1/e divided by 1 minus -1 over e. Get that. Let's multiply everything by e. Multiply the top by e, multiply that 1 by e, multiply the 1 over e by e, and there is our sum. So, this lines up with what we would expect. We are getting a negative answer because the very first term is negative and the magnitudes of the terms are going to 0. So the next term we're going to add to this, but we're going to add a little less than what this negative number is. So we're going to end up, the first term, if the series is alternating and terms are going to 0, the first term positive means it's going to be a positive sum. The first term negative is going to mean it's a negative sum. So we get a negative number there. Let's take a look at these. So we have already talked about these repeating decimals that are rational numbers, and we did an algebraic approach to get to the fraction, right? To get to that fractional form, we use a little algebra. Let x equal this thing. Here we'd multiply by 1,000, separate the decimals, subtract, divide. But these are geometric series. So let's treat it like a geometric series. This is a geometric series. So let's think of it this way. So we're going to think, I'm going to break this apart as follows. So we've got that. So I'm breaking it apart by groups of 3. And then let's rewrite this. Well, we should be able to just find A and R right away. A is the first. Do you agree, first off, I guess, that it's geometric?
Yep.
What is the A value?
0.7.
Yep, it's the first term. I'm going to write that as 37 over 1,000. That's the first term. And now the common ratio is whatever we did to get from the first term to the second or the second to the third, we multiply by 1 over 1,000. That's our common ratio. So we multiply by 1 over 1,000. So that is R, 1 over 1,000. So that is a convergent geometric series. It converges to A divided by 1 minus R. So A divided by 1 minus R. In my mind, the simplest way to simplify, multiply everything by 1,000. If you multiply everything by 1,000, we get that as our rational expression, fractional form of that rational number. So you could do the algebra way, but now we're in calculus. We're going to do the clever calculus technique instead of the algebra technique. The algebra technique's cool, but this is cooler. Treating it like a geometric series. So let's try this one. So with this one, we are going to focus our attention on the repeating part. We're going to take this 1.25 repeating. We're going to think of this as 1 plus 0.25 plus 0.0025, etc. So the infinite series part will be the 2,5 business. And then we'll add 1 to that in the end. So this is going to be 1 plus, and we are going to do an a over 1 minus r just for this part. So we're going to look at that part. And what is the a for that part? 0.25, which we're going to write as 25 1/100ths, or 1/4. And the common ratio, how do we get from one term to the next? Multiply by 100th. So that is the common ratio. So over here, we're going to do a divided by 1 minus r. Multiply everything in that fraction by 100 to simplify it. And we're going to end up with 1, which I'll write as 99 over 99, plus 25 over 99. So we'll end up with 124 divided by 99. Any part of that you are curious about, want to ask about?
Actually, I guess I have a question.
Yeah, ask.
It doesn't immediately start repeating, so if it's like 1.35, then 2.5 repeating, then you just do the same thing?
Yeah. So wherever the repeating part is the part that we're going to peel off and approach it with the geometric series, anything that sits in front. So if this had, let's just make it 1.3, 25, 25, 25, we would pull a 1.3 to the front and write that as 1 plus 3/10 plus the geometric series.
Okay.
Yeah, so you just want to peel off anything that's not part of the repeating, use that as a separate addition. Okay, so geometric series in the bag. We're done with geometric series for now. So geometric series are the first example of a series that we can find S sub n. We can find the sum of the series. If you can find S sub n, you can find the sum of the series. The second type of series, there's only 2 that we are going to look at, is called a telescoping series. So it's the other type of series that we can actually find S sub n and then take the limit of S sub n. So for this telescoping series, we are going to do the following. So here's what a telescoping series looks like. So it's similar to a geometric series in that we can find a formula for the nth partial sum, S sub n, that allows us to take the limit and find the sum of the series. Okay, so most series we cannot find S sub n, but for geometric and telescoping we can. So let's see what this looks like. So S sub n is the sum of the first n terms. So let's write out S sub n. So this thing, and you'll see why we call this a telescoping series in 1 second. So S sub n, sum of the first n terms. Now this one is we're fortunate, this starts at 1. If it starts at 1, we end at n. Right? If we're going to do the first n terms, we start at 1, we end at n. That's cool. So we're plugging in a 1. Our first term is going to be a third minus a fourth. And I'm going to put parentheses around it. That's the first term. The second term, now we plug in a 2, and we get a fourth minus a fifth. And then we get a fifth minus a sixth. For most of these, writing out the first three terms is enough. And then we're going to put some dots. And then we're going to write out the last two terms. I'm going to put the index value down below. So this is the k value. So k was 1, and then k was 2, and then k was 3. And the very last term in S sub n will be when k is n. What will the k value be for the term 1 prior to the last term? N minus 1. So k will be n minus 1 for the term prior to the last term. For most of the telescoping series that we do, if you write down the first three terms and the last two terms, you'll be able to figure out the cancellation pattern. So you're already sort of seeing, I hope, that, oh yeah, it's telescoping in that there's this sort of collapsing of all these middle terms, or most of the middle terms. So that's what they mean by telescoping. Like we see this cancellation pattern here. And this negative 1/6, that's going to cancel with something over here in the dots. All right, so that's what we mean by telescoping. It's collapsing down. So let's write out the last two terms here. So plugging in n minus 1 for k. So n minus 1 plus 2, we're going to end up with 1 over n plus 1 minus, plug it in right there, n minus 1 plus 3, so we have an n plus 2 in that denominator. And of course, when we plug in an n, it's pretty straightforward. We're just replacing the k with the n. So we've got that. So it's helpful to look at this cancellation pattern in the front. When we're moving left to right, we're going to cancel second part. I'm going to think of the term as having a first part and a second part. So here's the first part, here's the second part. The second part is going to cancel with the first part of the next term. We're going to continue like that. First part, second part, first part, all the way through. Second part, first part, canceling. Now if we change our perspective and we move from right to left, so let's come right here and go this way, because at the tail, it's not really the tail, at the end here, we're going to be moving this way. So if we move from right to left, we are canceling firsts with second part of prior. Canceling first with second part of prior. So here we're canceling the first with the second part of the prior. So this first, let's get rid of that blue one. So we're going to cancel this first with second part of prior. And then this first will be canceled with second part of prior somewhere in the dots. So only the 1/3 and the negative 1 over n to the, that thing, that negative 1 over n plus 3. Those are the only two terms that are not going to telescope out. Just two terms. So this allows us to conclude that S sub n is going to be 1/3 minus 1 over n plus 3. So there is S sub n. So on the test, you're definitely going to be asked to find S sub n. So we want to find S sub n, and then we're going to find the sum. So S is the limit of S sub n, and what is that limit as n goes to infinity?
1/3?
Yeah, 1/3. So that's going to be the sum of the series. So we found S sub n and we found S. So that's the nature of a telescoping series. We have a bunch of terms in the middle that just wipe each other out. Usually we have a couple at the front and a couple at the back that are preserved. And a chunk in the middle that just vanish. Okay, so let's do one more. I want to change this one a little bit just because I want to make it a little more complicated. So let's, instead of this one starting at 1, let's have this one start at 0. So if it starts at 0, S sub n's meaning never changes. S sub n means the sum of the first n terms. That never changes. But if the index is not starting at 1, then we have to be a little careful. So here's how we're going to be careful. So S sub n is the sum of the first n terms. So first, we're starting our index at 0. So we're going to have 1 minus 1/2. This is the first term. So here's, I'm not going to put a k here, though. I'm just going to put a 1. So that's the term number. That's the first term. So the first term is corresponding to k being 0. And the other one, k also counted the terms. Here's a little different. So that's the first term. The second term is found when k is 1. When k is 1, we get 1/2 minus 1/3. So this is the second term. Maybe I'll put a number in front just to emphasize that it's number 1 term and then the number 2 term. And then the number 3 term is going to go here. The number 3 term is found when k is 2. When k is 2, we have a third minus a fourth. Plus the dots. And then we want 2 terms at the end. So we want the n minus first term, and we want the nth term. Now here, we plugged in k equals 0. Here we plugged in k equals 1. Here we plugged in k equals 2. What is the k value for these two, for this one first?
K minus 1.
Nope.
Infinity minus 1.
Say again?
Infinity minus 1?
Nope.
N minus, or N.
So let's see, how did we get to the green from the red?
1 less.
1 less. So this is going to be n minus 2. And then this is going to be n minus 1, yeah. So we're plugging in a k value. The k value has to have n's in it, right? So we're plugging in, like in this one up here, the nth term, because this started at 1, the nth term is found by plugging in k equals n. And to plug in n minus 1, we will get the n minus first term. To plug in k equals 3, we get the third term. So here, k and the number of terms, they match, right? The number of terms and the k value are identical. But down here, the number of terms is different. So that's what we get. So let's plug those in. So we're plugging in k equals n minus 2 to get the n minus first term. So if we plug in n minus 2 right there, we have n minus 2 plus 1, so we have an n minus 1 in the denominator. N minus 1. And we plug in an n minus 2 here, n minus 2 plus 2, so we get a 1 over n. And here, plugging in an n minus 1 to get the nth term, n minus 1 will give us a 1 over n minus 1 over n plus 1. And now let's look at the telescoping piece of it. So second part with first part of subsequent, second part with first part of subsequent, second part with first part of subsequent. And then we turn around and go backwards. To go backwards, first part with second part of prior, first part with second part of prior. First part with second part of prior, first part with second part of prior. And so this one matched kind of identically the first one we did, where we just have 2 things left. And you can tell how many things are left at each end by the difference in these denominators. If those denominators have a difference of 1, you're going to end up with a front term and a back term. If the difference in these denominators were 2, you'd end up with 2 terms in the front and 2 terms in the back, etc. If the difference were 3, you'd get 3 and 3. So this allows us to conclude that S sub n is going to be 1 minus 1 divided by n plus 1. So there is the partial sum formula. Let's just check. If we want to get the first term, the very first term in this series is 1/2. 1 minus 1/2 is 1/2. So if we plug in a 1 right here, we should end up with 1/2, and we do. If we wanted the sum of the first two terms, we should get 1, these would cancel, 1 minus 1/3 is 2/3. So if we plug in a 2, we should get 2/3. Do we? Plug in a 2 right there, we get 1 minus 1/3, which is 2/3. So that'll match.
And can't you also, combine the fractions, make it n plus 1 minus 1 over n plus 1? And just n plus 1?
You definitely can do that.
Shouldn't.
Usually
the
we
limit.
don't, just because the limit's easier to do right now.
The limit's way easier when it's not.
Right, the limit's going to be easier when it's not combined, so we'll just, that limit is what?
1.
1. So the sum of that infinite series is 1. All right, so you all try this one. So that is a telescoping series. Maybe I'll do the first step. The first step, if it's telescoping, you know that you need to have a subtraction, and this one is just kind of hidden. So there is your infinite series. It would be nice, but usually we don't do it, to put parentheses around this entire summand. Usually we don't do it, but okay, so see if you can get that one. So write out your S sub n. This one starts at a counter of 1, so that's the easier case, when the counter starts at 1. See if you can find your S sub n. Today the first day of March Madness? That's why Dustin is missing us. He went off for some March Madness party. Priorities.
Exactly, done right.
Where's Christian today?
Oh, he flew to Atlanta today.
Oh, today he's on
Yeah.
And Matt is sick. Hopefully not too sick.
For this one, it feels like it'd be more intuitive if you flip the terms and put negative lnk first and then plus lnk plus 1, because then they actually line up in the same way the other ones did.
Could you do that?
Or pull out a negative and then just.
Yep, you could factor out a minus too.
Yeah. The intuitive order of.
Yeah,
plus,
'cause then
minus,
the-
negative, but
Right, because then the ln k plus 1.
is at the back and then
The back,
line
yeah.
up in a way that looks right, but it really doesn't matter.
So the main thing with S of n, you're adding up the first n terms, we just start by plugging in k equals 1. So we're going to end up with natural log of 2 minus natural log of 1. So there's our first term. And here the k value and the term value, these are both the same, right? The term number and the index value always match if you start at 1. So there's our first one. And then our second one, we're going to plug in a 2, so we're going to get natural log of 3 minus natural log of 2. So here we're plugging in a 2. Here we're going to plug in a 3. When we plug in 3, we get ln of 4 minus ln of 3. That's usually enough, then some dots, and then get to the end. And once again, if we start at 1, then it's pretty straightforward. Then this is going to be plugging in n minus 1 and plugging in n. So that'll be the nth term out there. So plugging in n minus 1 right here, that's going to give us n minus 1 plus 1, that's just n, so natural log of n, minus, plugging in n minus 1 here, natural log of n minus 1. And then we're going to plug in that, just the n. So it's going to look identical to that, except with an n instead of a k. So we're going to have natural log of n plus 1 minus natural log of n. And then we just want to go to the, that's already at 100%. Okay, so then we are going to do our cancellation. So the cancellation in this case, we've got first part with second part of subsequent. So first part with second part of next. And then we keep on doing that. So first part with second part of next, first part with second part of next, which will be in the dots. When we go backwards, let's start right here. When we go backwards, we start here, we see its second part cancels with first part of prior. Second part cancels with first part of prior. Second part cancels with first part of prior, which is in the middle. So our S of n, we have a minus natural log of 1. And the only thing down there that's not disappearing is natural log of n plus 1. This, of course, can be simplified. Natural log of 1 is 0. So this can be simplified to this as our S of n. And what does that tell us about S? So this is going to diverge to infinity. So this one diverges. Let's do one more of these. Let's shift it again though. It's good practice to do them shifted because it's a little bit harder. So let's make that start at, let's not start at just 0, let's start at 2. Let's start at 2. All right. So when we go to build our S of n, the first term, we plug in k equals 2. So that's going to be the square root of 3 minus the square root of 2. There's the first term. And this was with a k value of 2. And the term number is 1. Then let's go to the next term, second term. So the second term, we're going to plug in a k value of 3. So we're going to get square root of 4 minus square root of 3. So here we're plugging in k equals 3, and this is the second term. Then we're going to have a 4 for the third term. So plugging in a k value of 4 is going to give us root 5 minus root 4, and then some dots. All right. Now down here at the end, let's start with green because that's the counter. We're going to have our n minus first term and our nth term. And what will the k value be that we're going to plug in here? N and n plus 1. So let's do that. So if we plug in n, that one's simple. That's just going to be root n plus 1 minus root n. Plug in n plus 1, we're going to get root n plus 2 minus root n plus 1. All right, so there is the sum of the first n terms. Cancel out with our pattern here. First part, second part of next. First part with second part of next. First part, second part of next is in the dots. Come on, stop. All of a sudden it's getting grabby at the very end. Okay. And then if we go backwards, if we go from right to left, start here, we're doing second part with first part of prior. So second part with first part of prior, second part, first part of prior, somewhere in the dots. So the only stuff remaining, S sub n will be negative square root of 2 plus square root of n plus 2. So there is our formula for the nth partial sum for the finite series. And this will tell us that the sum of this infinite telescoping series is infinity also. So that one diverges too. All right, any piece of the organization there? It's really helpful to give yourself space, write it out, keep track of the k value, keep track of the term number. It's easiest when those both align. If they don't align, just be careful. So let's go back in time.
Kindergarten.
No, that's not long. No, when we're going back in time, we're going back centuries. Going back way, way far away. So this is called Archimedes' quadrature of the parabola. So prior to calculus, one of the most practical things in calculus is that you can find areas of shapes that have curvilinear boundaries. You can find all sorts of areas precisely. Long before calculus, and who knows if Archimedes did this first, but it's at least attributed to him because he was a beast. So the idea was, let's find the area of this parabolic region. And so what was done was the following. So an equilateral, a triangle was created right here. It's not necessarily equilateral, but that triangle was created, A sub 1, it's an isosceles triangle. That's created. And then subdivisions here and here of the segment to the right and the segment to the left, those two triangles were created. And then that's repeated again and again and again and again. So then we're going to subdivide here and here. That's going to create a little triangle up here and a triangle over here on the side that is going to look like a mess. So do the same thing on the right, and we're going to keep doing that. Keep subdividing and creating these triangles. And so they call this it's a method of exhaustion, where you're just going to slowly creep and get all the area filled by these triangles that are going to be filling in all the little spaces to create that full parabolic region. The number of triangles doubles at each stage. So we have one triangle here, the next time we have 2 of those, the next time we have 4 of the a sub 3's, etc. They're going to keep doubling the number of triangles. Now, the crazy part is this, that you can calculate, and this is not that hard to calculate, you can calculate that a sub 2 is exactly, the area of the blue is exactly 1/8 the area of the pink. That's not hard to calculate. With a little practice, you could do that with putting in some points and you could figure that out. What's amazing is that that pattern continues. That a sub 3 is going to have an area of 1/8 a sub 2. Now proving that is the hardest part. It's not terribly hard, but that is harder than showing those two. And so what you can then do is write every single area. So this is going to be 1/8 a sub 2, which is 1/8 a sub 1. You can rewrite this whole thing so that everything is in terms of a sub 1. So if we replace this a sub 2 with 1/8 a sub 1, we're going to get that. So replace the a sub 2 with 1/8 a sub 1. Replace the a3 with that, and we get this, etc. And all of a sudden we realize that it's a geometric series. If we simplify everything here, we factor out the a sub 1, that's a 4th, simplify this, so there's a 4th right there. Factor out the a sub 1, we get a 1 and then a 4th. Simplify this, simplify that, simplify that. We get this geometric series where the a value is 1, the common ratio is 1/4, and we get that the total area then is whatever the area of that original isosceles triangle is, the total area is just 4/3 times the original triangle's area. So if we just look at one example here, we've got this regular parabola open upside down, blah, blah, blah. The area of this original triangle is 1. 4/3 times 1 is 4/3, okay. That's the method of exhaustion. Then we go do the standard calculus method, we integrate it, and we get 4/3. So, prior to calculus, you could actually find the area of a parabola. As soon as you make that more complicated, obviously they weren't finding areas. But for the area of a parabola, you could at least use a geometric series. And you're going to see lots of applications with geometric series as you continue on.
And I do believe a very similar method was used to figure out pi.
Yes.
Based off like a circumscribed and a whatever it's called.
Inscribed.
Inscribed and circumscribed
Polygons.
polygons.
Yeah, regular polygon on the inside, the outside, let the sides go to infinity.
You can figure out that pi is it's basically the squeeze theorem actually.
Yes.
Pi is between
The
3
outer,
and 4 because it's a circumscribed triangle length side 1 and a 2 for the square.
right.
Basically figure out the circumference radius.
I use the integral to prove that right.
All right, have a great weekend.
Yeah.
Ciao now.
See you all next week.
Right, so I evaluate the integral, definite integral, and prove that that.
You did.
Yes.
Math is right.
Or my integral calculation graph.
Your calculation is perfect.
That's fair.
Perfecto.